composability. Jack, why don't you start us off about whole program compile?
Sounds good. Can you guys hear me and see my screen?
Yes.
Okay, good. So hi everyone. So I'm Jack from the PyTorch X3 team in Google. So I want to talk about something I call Torch Dynamo single step graph. Um, so just kind of start us off, like what is this? So I think today we all know that Torch Dynamo, you can capture the PyTorch model in the FX graph, but it captured the forward on its own. So this is today's workflow. Well, I think more or less. So Dynamo capture the model forward and it sees the lost step backwards. It's going to do a graph break. And then it's going to let AOT autograd to use makeFX to compute the backward, which I think originally was single graph, and then do the split. But as a result, that the compiler backend like X-ray, we get two graph, or at least two graph for a single model training step. So which is the forward graph and the backward graph. I think this is not an issue for inductor, but for compiler like X-ray, like this will have some regression in speed because on lazy tensor we usually get a single step graph, and X-ray compiler in general expect a single graph. By splitting the graph, it will introduce like eliminate some of the fusion opportunity, and at the same time, it's going to increase the graph launch overhead because the whole X-ray and TPU wasn't designed with launching multiple kernel very efficiently. It was kind of expecting launching one kernel per training step. So that's one difference between hardware and compilers. So this has been a problem for us for a long time, and I would say this is probably the biggest issue preventing like PyTorch X-ray um, using the Dynamo as a default training backend. So what we want is we want Dynamo to be able to admit a single graph for each training step that includes a forward, backwards, and optimizer. But in this design, I only talk about forward and backward. I haven't really have time to look into optimizer yet. So this was the original workflow, and this is the proposed workflow. So we use the compile autograph. So most of you probably already know the compile autograph. It's very handy. I think Jason implemented. Thanks a lot. So compile autograph was able to convert the C++ autograph into the FX graph. So with that, I think Ed and I, we did some brainstorming, and like one idea we can do the single step graph was we let the Dynamo capture the forward, and when it sees the backward, instead of graph breaks and then use AOT autograph to directly generate the backward, what we can do is we use AOT, we use compile autograph as a context manager to capture the backwards, and then compile autograph will emit a FX graph that was representing the backward of the model. And because FX graph itself can be executed as a normal Python function, so what we can do is like we can just let Dynamo inline that FX graph as if autograph happens in Python. So in my opinion, like the biggest reason why we couldn't really directly let Dynamo to consume the backward was because backward was happening in C++, like the autograph. So compile autograph kind of does that transformation for us. So now from high level standpoint, it's as if like backward and forward, they all in Python. So we can just inline the whole thing. And then as a result, we can emit a single graph that contains both forward and backward. So I'm going to pause here, like just in case that I miss anything and that explanation makes sense. Okay, if no question, I can just keep going.
Actually, I just want to point out a counterfactual, which is that you didn't have to do it this way, right? Like if you're like, I don't want to use compiled autograd because that seems weird, then like you could have figured out how to implement backward by hand, like implementing a backwards in Python, for example, and that is also a like feasible alternate way to go about doing this. Although we thought this was worse than using compiled autograd, so we did that. Question from NYC.
Um, so AOT autograd gives you the forward and a backward, like in an FX graph. Like, why wasn't that sufficient?
So I'm asking like, why don't we just stitch the graph, let's the forward and backward and just be done with it.
Sure.
Then we have a single
Yeah.
graph.
Yeah. What is wrong with the current flow? Sorry if you explained already.
No, I actually asked that question to Brian Ed a couple times. I think it's mostly to do with hook. Ed, do you want to comment more on that?
Let me think. Okay, I think there are a few levels of answer to this. So one is that you can't just use AOT autograd because AOT autograd poops out this autograd dot function, right? So like, it's not exactly the right thing, right? Like if you want to fuse the forward and backward together, then you actually just need a straight line like thing that goes all the way, including the forward and backward. But okay, whatever. Let's say you do that, all right? So then you have another problem, which is, well, okay, how do I integrate this with Dynamo, right? Because Dynamo is like going along and it's like processing all these things, and it has a backward call. And then it might want to keep going, right? Like Jack eventually wants to hit optimizer. So he needs to keep going even after he's done processing backward. And all of the Dynamo state has to be in the right order so that Dynamo can keep going in that case. And so, can you do that with like MakeFX AOT autograd style? Well, you probably can. And so we're actually talking about another counterfactual proposal is it's like, okay, so I'm Dynamo, I've got a bunch of operations that I've traced, and I hit it backwards. And then what I want to do is like, I'm going to somehow replace this the like set of ops I've traced already with like the MakeFX trace version, like in place, like, swizzle the graph to put in the new thing, and then like, run around like getting everything to hook up to the same place it did before, and then keep going Dynamo afterwards. We didn't do this. There might be good reasons to do this, but this is not what Jack did in his prototype. Did that answer the question?
Sure. So I'm hearing that like both approaches are feasible, but we just picked one because
we
we
picked
wanted
using
to.
compiled
But
autograd because
sure.
okay. So and now the hooks thing. So Jack's thing about hooks is that, well, if you've got arbitrary Python code in hooks, then when you do it the compiled autograd style, you can actually trace through the hooks with Dynamo and like do them safely, including with like Python state mutation, right? Whereas if you're doing MakeFX, you're just screwed. You just can't you can't deal with arbitrary blobs of Python code in backwards.
Makes sense.
Wan Chao, you had your hand raised briefly. Did you want to pipe in?
Oh, yeah, I just want to point out like I think the other reason is that why we can't directly use AOT autograd is that there's some certain ops are missing between the forward and backward. Like when we trigger the backward call, there's usually a loss function, and when we call torch compile beforehand, like on a module, like we don't know the loss function, so that ops is kind of missing there.
All right, Jack, carry on.
All right. So this is the high level design. So I will show a breakdown of like what change I actually did in my POC, which I think I have the link somewhere. So this doc is not ready. When it's ready, I will share more broadly. So pretty much, I will say what I do, and I'll explain later why I need to do all of this. So pretty much, I need to inline a bunch of stuff, like all of the modules for a function. I actually need to inline all of the torch function. Let's not like, for example, any op that's composite implicit autograph need to be keep inlining until it hits something that's more or less call it an op, like couldn't further decompose. I need to inline the loss function, and like accumulated grad is also give me some issue. I also need to inline, and I need to create a mapping from fake tensor to tensor variable. I will talk about why I need to do that. And the biggest part is I need to inline the tensor dot backwards until I hit the torch.c engine base.run backwards, which is a PyBind. And when I hit that PyBind, that's the place where I use compile autograd to actually run the backwards. So now that's a high level. Let me just go into the detailed design. I'm not going to go in the same order. I'm pretty much going to go the order like how I implement stuff. So give you a sense that when I implement something, something doesn't work, so I have to implement another thing. So the first thing is on today, like when we see the tensor dot backward, pretty much the Dynamo just going to throw an unimplemented error and just do a graph break. Then what do we actually want to do is that we want to let Dynamo keep going. So pretty much when Dynamo sees the backwards, it's going to create torch variable like tensor.backward and then just execute that. That will allow Dynamo just keep inlining. Eventually, Dynamo will hit like this torch.c engine base like that backwards. Pretty much that's with a pipeline that we cannot inline anymore because this function is a C++ function. So now then what do we do? Ignore the first part first. So pretty much what we need to do is this. We create a compile autograd context manager, and within this manager, a context manager, we run the backward. The one thing I want to point out is like I also include all of this. So the input to all of the, when you are tracing in Dynamo, all of the input, like all of the tensor input, they come in as a tensor variable concept. Like all of the thing, the Dynamo C should be a variable checker, and tensor variable is one of the variable checker. But with under the compile autograd context manager, we actually want to run the backward. But you cannot run the backward with tensor variable. You need to run it back with some kind of tensor. But luckily, each tensor variable actually have an example value, which is a fake tensor. So pretty much what I do here is like I convert all of the tensor variable to the fake tensor by accessing its example value. And I believe all of this like example value will actually going through the whole forward. So the autograd is actually being set up correctly. Autograd check this like the fake tensor correctly. So when you actually run the backward, you will run the backward in the correct order. So that's how we actually get the compile autograd working. So here's a graph, which I think is not 100% correct, but in a high level, it kind of tell us what compile autograd do. So here I would say it's a typical scenario when you run a compile autograd, if like discard this project. So just compile autograd itself, when you run the tensor.backwards, or like just the backward function under compile autograd, usually give you a real tensor. And then compile autograd will give you two things. It will give you an FX graph that was representing the backwards, and also going to give you all of the tensor inputs for this FX. So effectively, you can just run this FX graph as a Python function, taking all of the tensor input, and then it's going to give you all of the outputs. I think they are just the gradients of all of the tensor. But I think it also changed, but right now FX graph also include accumulated graphs of the grad assignments in place, but just assuming that isn't the case. So pretty much compile autograd, it can extract the FX graph representing backwards and give you all of the tensor. So now, how do we use it differently? Well, we use it differently that we didn't use a real tensor to run it backwards. We use a fake tensor to run it backward, but those fake tensor, they was being checked by the autograd, so they can actually emit correct graph. So what compile autograd give us is two things. The one is the FX graph, that's the same, but it's also going to give us the tensor input for the FX graph in the fake tensor format. It makes sense, right? Because we run the compile autograd with the fake tensor. So it's going to give us all of the tensor input as fake tensor. Then what we want to do is that instead of executing this backward graph, we want to let Dynamo inline this FX graph as if it's just a Python implementation backward. But then here comes another issue that you cannot just inline things with fake tensor. Dynamo, like I said, Dynamo expects everything to be a tensor variable. So now the problem becomes, how do we convert this fake tensor input for the backwards back to the tensor variable? I'll talk about that later. Now, assuming we can just do that conversion. Now we have the FX graph and we have a tensor variable. Now let's just treat this whole thing as just a Python function and just inline. And in the ideal world, everything just work. Now we have a single graph that's representing a forward and backward. From Dynamo perspective, you see a bunch of like Python code for the forward, and then you see another Python code for the backward, and just be done with it. I'm going to pause here in case there's any questions. Okay, if not, I can just keep going forward. So here is a simple example of the MNES. So I just want to illustrate one thing that we said that first we need to convert the tensor variable to the fake tensor that was usually the loss, like you usually call loss backwards. And then we need to convert like the whatever tensor that compile autograd return, and it return as a fixed tensor format, we need to convert it to a tensor variable again. They are not the same tensor. Like the tensor that goes to the tensor variable to fixed tensor, that's usually the loss tensor. It's usually just one tensor. But the tensor that Dynamo return to us, it's usually a lot. So here's an example of MNest. It's a very simple model. And the backward graph always says forward is actually backward. The backward graph that compile autograph return to us looks something like this. You have 23 inputs. And it's going to run a bunch of functions. Eventually, you will call the accumulate grad.default. So how do we interpret that? Which, if you think about it, actually kind of makes sense, right? Because in the forward function, when you're doing the forward, autograd is actually going to save a lot of intermediate activation for the backwards. And all of those tensors that being saved by the autograd, eventually they will become the input to the backward graph, because we need all those intermediate tensors to compute the backward, and all of them will be returned as a fixed tensor format. So that's what we do. I just want to avoid the confusion of like, if we just do the conversion and everything should just work. It does not. So that's that. Creating a fixed tensor to tensor variable mapping. So because tensor variable to fixed tensor, like it kind of just comes for free, because every tensor variable like has a proxy tensor, and the proxy has a sample value. So for any tensor variable, we know how to convert it to the fixed tensor, but we don't know how to do the vice versa. So like when it's a fixed tensor, how can we convert it to a tensor variable? Well, there are two parts. Let me talk about first part. Let's say we actually, the one thing we can do, the most obvious thing is every time we create a tensor variable, we know like this tensor variable will have an example value, which is fixed tensor. We can just create a reverse mapping, which is kind of dumb version I did here, just tensor dit. Every time we create a tensor variable, we also create a mapping of the fixed tensor to the tensor variable. But that's a catch.
Question from NYC.
It only works. Okay, go ahead.
Yeah, sorry, just to go one step back. So you get a graph from compiled autograd, which is the thing a few things above. Yeah. What do you do with this graph? Like, do you just inline it into the Dynamo graph, or do you do something else with it?
Yeah, I actually just inline the whole thing.
You inline it into the Dynamo graph.
It's just a Python function. Yeah.
Actually, hang on, Jack. Aren't you stepping into it using Dynamo, or you're actually just plopping it in an output graph?
Sorry. When I say inline, I think I call like the tx.instruction translator. I think pretty much it's going to step through this function one by one.
So we're actually going to end up stepping each of these in symbolic convert.
Okay, that's pretty cool. Thanks.
All right. Okay, where was I? Okay, I was talking about like this conversion. So pretty much whenever we create tensor variable, we just create a reverse mapping. But let's catch. We only knows how to convert the fixed tensor to the tensor variable if we actually create a tensor variable for it, which means that this tensor needs to be seen by the Dynamo in the forward somewhere. This might sound obvious, but let's explain like what might happen. So let's use the MNest as an example again, a relatively simple model, ReLU, Maxflu2D. And this is the forward graph that's being captured by the Dynamo today, like in default. Like you see, it mostly represent a graph. It has the functional Maxflu2D, it has the FC2, which is just the linear. But there is a problem of this whole approach. That's because like the composite implicit autograd. So the Maxflu2D under the hood, it actually got decomposed into the Maxflu2D with indexes. And Maxflu2D with indexes, it returns two results. The one is the original result, Maxflu2D also return indexes. And the problem of that is the indexes, it's actually going to be safe for the backward, which also makes sense. But now here's a problem that the Dynamo doesn't see the Maxflu2D with indexes. In the Dynamo, like this forward graph represents everything that Dynamo sees. Dynamo only sees the Maxflu2D. So it doesn't know anything about the indexes also being returned under the hood, so it cannot create a tensor variable for that. but that tensor is being used by the backwards. So now we have a problem. In the backwards, we need some tensor variable that does not see by the dynamo. So now that's kind of conflicts. So then I kind of run out of time of writing a doc. Like I only started writing this doc yesterday. So let's just go back. So that's why I ended up need to do a lot of inlining. So pretty much we say, okay, dynamo today it stops relatively early. Then when you see something allowing graph, it stopped. But in order to make this whole design work, dynamo actually need to keep further inlining, even like torch function, like torch.maxput2d, until it hits something that's not, it cannot decompose any further. The same thing for a loss function. So I'm just going to pause here in case there's any questions.
Jason.
Yeah, so there's a few potential pitfalls that I think are solvable, but you didn't mention, so I want to call them out to make sure that you're aware. So one is that in some cases the autograd tape can have global state before dynamo gets called. So for example, if you do a bunch of eager ops and then you call into dynamo, it could be you could get in a state where the autograd tape has some operations already queued up in the autograd engine, and when you eventually hit that call to backwards, that backwards needs to include sort of the operations that happened in eager mode before you called into dynamo. The way I'd suggest fixing that is basically adding a new dynamo guard, which is asserting that the autograd tape is empty. Because I think that this is a case that it's probably fine to just not support, but we should make sure that we err in that case, not like either include the ops that were on the tape beforehand or ignore the ops that were on the tape beforehand. I think because you're using fake tensor inputs, you're going to just ignore the ops that were on the tape beforehand because you're using fake tensors, not real tensors.
All right.
But basically what I think we need is like a guard that the autograd tape is empty guard.
Right.
Which ask Alvin how to implement it. I don't know how to implement it.
Okay.
Then the other one is dynamic shapes. So compiled autograd is constructing its own dynamic shape variables. And I think there needs to be some way, and currently there isn't like a really good way to map where those things came from, because those dynamic shape variables are basically coming from integers in C++ often, and how to actually like bind the dynamic shapes together properly. I might so yeah, and so those are the two things I'd suggest. For the dynamic shape one, we might since it sounds like you're running with fake tensors, maybe the fake tensors would have siments on them already rather than concrete ints. But I say, yeah, I'm worried. I'm a little bit worried about the dynamic shape case and how that actually plays out.
Yeah, makes sense. I actually haven't really think about dynamic shaping. I consider that as a step going forward. But thanks for bringing this up. I'll also reach out to Alvin regarding that tape thing. All right. Any other questions?
Actually, I want to just call out the point Jack was making before Jansel's 2 points, which is that like under the strategy we have described here, we must inline into all torch ops, and not just inline to the C call, but we must also inline past the composite implicit autograd decompositions. Because if we don't inline that far, we don't actually have nodes for the intermediates in the graph so that we can actually like hook up to the rest. And that's a pretty big step. So like, you know, part of the reason why we're here is it's like, yeah, you know, this sounds great. You know, let's do it, even though it's a bunch of work. Or I hate it. Like, let's find another way. That's part of the question I want people to think about.
I almost want like that lowering. So like currently currently with other backends that are using AOT Autograd, that lowering that decomposition of composite implicit autograd ops happens as part of sort of the AOT Autograd tracing. I almost feel like we should be doing that lowering simultaneously to the backwards capture, where like where we don't need to sort of like maybe like basically like maybe we need like a separate Dynamo context for that lowered version, rather than trying to map it back to the original one. Is that making sense?
I don't feel like I fully follow. So what do you mean, like in the backward, we need to like pretty much like have its own mapping of the decomposition?
So like I'd almost like break the problem into two steps, where like step one would be capture a whole program graph that includes a call to loss.backwards in the graph. But
Jason, we can't, in the general case, we can't do this because the backward may call Python hooks, and we must process the Python hooks before we can keep going. I agree that in the simplified case where the backward is well behaved, this can work, but not in the general case.
Okay, I could be convinced of that.
Can you run Dynamo again after you've already run Dynamo?
I mean, if one of the hooks is like setting a variable from false to true.
That part I wasn't sure, so that's why like during the whole compile autograph thing, we actually doesn't exit the Dynamo. We just kind of call the compile autograph and then we go back to Dynamo and then just trace the whole thing. I don't know, just like as if like if we do a graph breaks, just like today what LT autograph do, I don't think we can re-enter the same Dynamo region, but correct me if I'm wrong.
This is a dumb question, but what are we going to use these mismatching tensor variables that we don't have access to for? Like, if we never made a tensor variable for them during forward, are we ever going to need them after backward? Or is it the case that we're taking on more responsibility for like updating them? I don't think we would be updating anything. None of these are going to be parameters, right? Like we won't be accumulating grads to them.
No. Yeah, pretty much anything missing there. Or so far, like on ResNet and MNet, etc., everything missing was the intermediate variable created by the decomposition. I think about the same question. I don't have a good answer. Maybe who could do something to it? Alban?
No, I have a question for Jason.
No.
Go for it.
Okay. I'm trying to rationalize what's happening here. How do we make sure that, you know, when we do the dynamo tracing, that the output tensor we have, does it have a valid grad function and a valid autograd tape associated with it, or is that not the case actually at the end of the symbolic interpretation from dynamo?
So for symbolic interpretation, we should not be creating an autograd tape for because like everything's done with fake tensors.
We actually do, because we like preserve requires gradness when we fakeify the real tensors, and then you will just get grad funds on them like naturally once the requires grads are set up.
Yeah, that's true. That's true. But it won't touch the original tape.
Yeah, it'll never touch the original tape.
So to what extent do we want to say here that this we want to make this tape building a full-fledged feature because this is what we want the inline backward to unroll, actually.
Yes. So like, a alternate plan is instead of like, building GradFun via the C++ mechanism, you re-implement AutoGrad and, you keep track of your own tape and then you can, play through it directly without using compiled AutoGrad.
No, what I meant is you seem to say that fake tensor is already using the C++ mechanism to build the AutoGrad tape for us today.
Yes.
Why can't we just use that tape to run the backward that is in line?
But that's what compiled AutoGrad does.
Isn't that what he's doing?
So I'm not sure then what is the problem. Like you should already have decomposed the thing you need decomposed because like composability
But those things are already decomposed, but the decompositions are not visible to the dynamo graph because the dynamo graph is done before decomposition.
So you have some fake tensors that appear.
Jack, can you scroll to the decomp example? The was it cross entropy? Log
was
softmax,
the max-pool 2D.
max-pool 2D, yeah.
Max-pool 2D. So pretty much this is what Dynamo see. Dynamo only see the max-pool 2D, but under the hood, max-pool 2D actually calls max-pool 2D with indexes. Dynamo doesn't see this, so he also doesn't see the the additional output that this decomposition has. But this tensor is neat for the backward, so now we have a gap.
Or like another example is like suppose you have a dropout. Internally, like dropout is going to create like the mask, and then that mask is going to get used in the backwards. But that mask is not going to be associated with a dynamo variable tracker, and so there's no way to reference the mask in the backwards.
Okay, so it's in that way then that the GradFN we generate is not actually a valid one, is because it might contain some fake tensor that are not associated with any nodes, and so it doesn't really make sense to use the object inside the GradFN.
Yeah.
Okay, thank you.
Remember, at the end of the day, we want a graph that has a bunch of backward calls. So like we need to have something like in the graph. So another counterfactual proposal that Jack and I talked about is, well, what if, when we get to the backwards, we just rerun the forwards, but like decompose so we can like get out like some sort of checkpointy style thing. This doesn't seem like the right thing to do, but like, it's another way you can solve the problem.
Yeah, pretty much we do gradient checkpointing by default.
I hate it.
Yeah. Any other questions regarding this topic? Like I think I have like one more point I want to be made. Then I think I'm done with this presentation.
Why don't you make your last point?
Okay. Let me actually just select this tab instead. Let me just show like where I am. Wait, I think this one just frozen. Okay. So this is a GitHub comment that's high-level change I will talk about. There are a couple of major issues that I may or may not know how to fix. So the first thing is actually it's more complicated. It's the detach. So pretty much what ended up happening is like we expect like if after we decompose everything, we would have expect every intermediate tensor is being captured, but it's actually not. In the case, for example, on a function like ReLU, that it has an output, and the output is also being saved for the backward. But what ended up happening is because to avoid the reference loop, like the AutoGrad doesn't save the output as a tensor directly, save the output.data or output.tensor data. And before running the backwards, it will call a detach on the output.tensor data. So effectively, what does it mean? it means like the input to the backward graph is a detached tensor, and the detach happens in the autograph C++ code that's not visible in the dynamo. It's just impossible to be visible based on current design. So now, even after we decompose everything, it's still possible that some of the tensor is missing for the backward. So what I ended up to do is like I just let dynamo to I just let autograph to save the original output, but then it's going to create a reference cycle. It's a hack, but I don't know how to fix this problem properly. Another problem is accumulate grad. So accumulate grad appear today in the graph to be a inductor op, which seems to work correctly on the CPU and the inductor backend, which I assume. But for some reason, it doesn't work on the X-ray backend. It just becomes a no op, and I don't know what's the proper way of to actually lower the accumulate grad in place. So what I ended up to do to unblock myself is I just implement a dummy accumulate grad. So pretty much every time we see the accumulated grad, instead of like capture this op in the graph, I just try to inline this function. But even inline this function, you have some issues. Like when so the first case is actually relatively easy. Just when a grad is none, you just do a grad assignment. Second one was like when that's already a grad, when you want to call accumulate grad, you just do an in-place add. But then there's a problem, like because like in the backward graph, the T1.grad will become the input to the backward graph. Makes sense, right? You want to do an in-place mutation. But T1.grad is not visible to the dynamo by default because you don't call T1.grad in any of the forward function. So that becomes a problem. Now we have another mismatch. Yeah, and I think the last problem is less severe. It's like now, yeah, we know we need to decompose the torch function, but what's the good rule of thumb? Like what function do you decompose? Do we just decompose everything? Today, that's kind of pretty much what I do, but I feel like we don't really have a good way of saying this torch function will eventually trigger composing implicit autograph, so we should decompose or we should inline. Otherwise, we don't need to. But now I don't know how to do that properly, so I try to inline everything. So those are a couple major issues I'm having right now, which I think I have workarounds more or less. But if we want to land this change, then we need to fix all this problem properly. So that's a challenge I'm facing. Yeah, that's about everything I want to talk about today. Any other questions, comments? All right. If not, I think I will just stop sharing. Go ahead.
Yeah, I guess I was curious how hard it would be to have accumulate grad not be an op and just be a thing that we trace through. And in my head, part of the reason that's difficult is because accumulate grad is really complicated. It has like 5 crazy edge cases, and that's a pain. And maybe if we just implement it in Python and trace through it and only handle the easy cases and error in the hard cases, that's reasonable, but I'm not sure.
Yeah, I don't know. So
yeah,
go ahead.
Yeah, I mean, I'm the one who made accumulate grad and op, and basically, like originally what I did was I did exactly what you're suggesting. I just sort of like built a Python version of accumulate grad and sort of faked it. And like the problem is like accumulate grad as an op has like many like two pages of code of like corner cases and edge cases, and they like peek at reference counts, and they like handle all these like sparse tensor layout things. So there's like all these like corner cases that were sort of like hard to replicate in Python. I think we could with enough effort, but basically the initial version, which sort of did like something similar to what Jack did, which is like a really simplified Python version of accumulate grad. It failed a bunch of test cases in the AutoGrad engine tests, and to basically get all the test cases to pass, I'm like, okay, I'm just going to use the real code for accumulate grad. I'm going to wrap it in an op. It's not really an inductor op. I just stuck it there because I didn't realize it was going to get used elsewhere, but it's maybe possible, but it's like there's a lot of annoying corner cases.
That's fair. Yeah, I got like the sparse example you gave. I think sparse blows up in a bunch of other places when we trace anyway, and maybe like the cases that are hard to trace properly for cumulative grad are similar to the cases we already know don't work today. But yeah, that would totally take work to look into.
Okay, now that people have had time to digest, I want to pull the room for vibes. So here are two paths Jack can potentially go down. Path one is to basically do what he just presented, and like we figure out how to like do all of the infra stuff to actually make it happen. And the biggest change to Dynamo is Dynamo learns how to inline all the way down past composite implicit autograd while it is tracing forwards. The other path I can imagine is something like, well, let's say that there's no hooks in backwards or some other simplifying assumptions, so that you basically somehow use makeFX essentially to like blart out the forward and backwards graph instead of going through compiled autograd. I don't think there's any reason to go through compiled autograd if you're like there's no hooks or anything like that. That seems like the other like reasonable path you would take. And I'm just curious what people's like temperatures on these things are. NYC.
I'm just curious, are there any obvious other sort of use cases you could get out of tracing through composite implicit autograd? Like, does it make anything else possible? Nothing obvious, it sounds like.
Well, to what extent do we need to move the whole part that is above autograd from AOT autograd up to Dynamo? Like, do we need to lift everything that is above autograd today in AOT autograd as well? Like, because...
But there isn't really anything. Right, like most of the AOT autograd heavy lifting is like functionalization, but that's below autograd. So on top of autograd, really all it is preparing the tangents for the partitioning. But you don't need that when you're doing backward as is, because you're not going to partition. You just want to run it and get all the operations out.
Well, you do need to go, I guess, all the way to the dispatcher and at least all the way to the autograd key in the dispatcher, right?
Yes.
So whatever is in the dispatcher above the autograd key now has a chance to run with that.
And so, for example, we don't do PyTorch today, but if we did do PyTorch, we would be expected to know how to get past all of that on the way to autograd.
I mean, like, definitely, like, I sort of agree with you, Ed, that, like, if there's no hooks, then in some sense, this is, like, a subset of AOT autograd. You can just take AOT autograd, you can comment out everything after, like, partition, and then you're done. It's essentially, like, easier than AOT autograd in some sense. So then there's the question of, like, okay, like, and like forward hooks, we already support in Dynamo, so it's really just backwards hooks that this gives you. And there's a question of, okay, like, why do we need backwards hooks? Well, probably the main reason we need backwards hooks is for distributed, because basically all the PyTorch distributed stuff makes pretty heavy uses of backwards hooks. In the specific case of XLA, I believe like XLA went and like re-implemented like XLA distributed without using backwards hooks at all. And so like maybe like XLA distributed doesn't need backwards hooks because they're just doing their own thing. I think directionally, like within PyTorch, it would be a lot better if we unified distributed on XLA with distributed in the rest of PyTorch. And I think it's actually kind of like a bad state that we have like XLA distributed looking nothing like PyTorch distributed. That's like a pretty big like bifurcation in user experience because users have to like do different things if they want to make their code distributed on XLA versus not XLA.
Yeah. Jason, I totally agree with you. So one reason I want to do things this way, like instead of just creating X-ray own things, I want to make this a thing that can be shared between PyTorch and PyTorch X-ray. And we are trying to get rid of any X-ray specific things. So I want to do it properly. So that's why, like, although we don't really use any backward hook, I want to support it properly. So it's landable and potentially one day it can become the default, at least like one valid option for the non-X-ray parts of the PyTorch.
Yeah, I think that's good. And directionally, I agree with that. I think that's the right way to go. But it's yeah. I think it is worth noting sort of that like in the current state of the world, like this is mainly for backwards hooks that are mainly for distributed.
Voss.
Do autograd functions fall into all the same problems as backward hooks? Isn't it like also all the same things because it's another user defined backwards?
That's true. Custom autograd functions have some similar issues.
Okay, thank you, Jack. I guess we have our answer. That's a lot of work going down the pipe, but I guess we'll figure it out. Sounds great.
Sounds good. And again, I just want to thank everyone who helped me to writing a whole project. I kind of learned Dynamo from scratch. So I want to thank Ed, Bart, and Brian and Will for helping me implement this POC. So yeah, thank you.
Okay, we've got 10 minutes left, so let's just do some rapid fire. So Jerry, tell us what is going on with uint 1 to 7, because a lot of people that.
Should I just describe the plan, or
yeah, tell us the plan.
Also the motivation and stuff.
If there's questions, we can answer questions.
Sorry, can you hear me?
Yes.
I think you cut out, Ed.
Yeah, I cut out.
You cut out.
Oh, sorry. Should I just describe the current plan for implementation, or also the motivation for the whole stuff?
Go ahead, Jerry. I think Ed's connection is a little spotty.
Yeah, I think Jerry, more of the plan of like what we want to do.
Okay. Yeah, so for the plan, basically we want to add the uint 1 to uint 7 dtypes to PyTorch core. And these will just be backed up by dummy C++ dtypes. And then the main logic for all these dtypes will be implemented in tensor subclass. And let's say like this include the implementation for like torch tensor factory functions like empty. We say like the way we will do it is to when the empty get a D type of like let's say uint 1, we will reroute to Python to return the uint 1 tensor subclass. And all these like different operations will be in this tensor subclass. Yeah, and I think that's pretty much it we want to do.
Questions, comments? I think one thing that I would add is we had a very long discussion in the FP8 chat about like when are we adding a D type versus when are we not, and I basically made up a rule, and I think it's a great rule, so I'm going to tell you all what the rule is, which is that if you say torch.tensor blah dtype equals your new dtype. If this is meaningful, then we probably can add it. Like, and there's going to be silicon for it, and like it's going to be widely used, or we predict it will be widely used because NVIDIA is releasing hardware for it. You can put it in. If you need extra metadata for the meaning of your tensor to be meaningful, it is not going to be a dtype, or specifically, it's not going to be a thing in the C10 scalar type enum. And like, so for example, qint should not have been a dtype because they're meaningless without the like actual quantizer. And so like you have this dtype, but you can't use half of the PyTorch APIs on it because they don't make sense because you're like missing metadata. Similarly, FP8 is a dtype, but only because our dtypes are the unscaled FP8, right? If you have scaled FP8, that's its own thing, a tensor subclass separate from the base support, which is unscaled. It doesn't have any other extra metadata. And then there was this other interesting data type MX4, I think, which is basically you get a bunch of numbers and you have a shared exponent for them. And that one also is not going to be
Avik, you are not muted.
Ed's frozen for everybody, right?
Yeah, Ed is frozen again.
Sorry.
But MX4 is very cool.
That's all.
And one caveat, it's you can interpret a single element of that tensor as a real number equivalent, not necessarily the entire tensor. I mean, it's one way, but is that good refinement, Ed?
Scalar type in C++ is always about a single element.
Yeah.
So yes.
That's the right.
Okay,
And
well that was easy. Go ahead.
just to confirm, so for that distinction, like all of those dtypes, both like scaled versus unscaled things like split 8, and then also uint 1, 2, 3 through 7, is the idea that they'll all be represented through subclasses, but some of them require extra metadata, aka the unscaled dtypes, and some of them do not require extra metadata, aka uint 1 through 7, and that's the distinction you're drawing.
Oh, the reason why uint 1 through 7 are going to be implemented as Python subclasses is because none of our C++ infra works with sub-byte sizes. So I'm just giving up. I'm just like, whatever. We're going to do it in Python because I don't know how to do this in C++. And I don't care.
Yeah. So like by your rule, they could be details.
They could be in C++, but like, you know, basic shit like, oh, I want the address of an element doesn't work anymore.
Yeah, and I think, Brian, as well, in this worldview, the way FP8 work is like, we have some float8 whatever dtypes that exist and do make sense. These are the unscaled FP8 dtypes. But we explicitly are going to say they exist. They are scalar types. They are a valid thing we could do, but we decide not to do anything with them. And so, we're going to say, yeah, these dtypes are here, but we're not going to provide you with much implementation for them. If you want to do anything that is, an actual float8 use within deep learning things, you want to use the scaled version, and the scaled version is that other thing altogether. That is going to be.
Wouldn't the subclass use the dtype like as a substrate?
It will, yes.
For uint 1 through 7, are those going to be scalar type entries? No. Was that the right?
They will be, yes.
See, like if I think of an FP4, I think, okay, well, the scalar type entry could be uint4, and then the actual like metadata needed could be wrapped up in the tensor subclass. Like I think there would be an argument to say like, oh, you already have uint4, we don't need to have an FP4. Just use uint4 and then interpret it the right way in your tensor subclass. But then the silicon argument comes in.
Yeah, so let's just talk about any4. So with any4, what will actually happen is you'll have two subclasses. You'll have the uint4 tensor, which is like the storage, and then the any4, which also gives you the metadata for the lookup table. And so it's important to say what exactly you're getting from having a uint4 tensor. What you are getting is just the sub-byte arithmetic and viewing operations. That's really all you're getting. You're not getting much more on top of that. So most of the like heavy smarts is going to be in whatever the actual quantized subclass is going to do.
What do you get for having a scalar type entry?
It means you can say torch.uint1, and in particular, when we make the subclass, we need to give it a dtype. And so if we don't have a scalar type entry, then there's no dtype to give it. Now, you might ask, if I have any4 as a tensor subclass, what should its dtype be? Don't I need an any4 dtype for that? But I just said no, you're not allowed to do that. And in fact, this is basically what Alvin proposed, you should just say it's float. Because really what you have is you have a float tensor, but its internal representation is compressed in a particular way.
We gotta go. See you guys.
See y'all.
See you. Thank you.
All right, that's the end of composability. See you all next week. Cheers.